Okay, let's continue on with the time series theme. Whenever we are doing cross-validation on time series data, we have to be careful. We can't just randomly assign data points to our training set and then randomly assign data points to our test set. When we're dealing with cross-sectional data, that makes sense, the random assignment does. However, it does not make sense when we're dealing with time series data. Our splits have to be time aware. For example, we don't want to get in a situation where, for example, we have trained on some data from January 2023 in our training fold, and then in our validation fold, we have data from December 2022. That's not a realistic scenario and would not give us a fair opinion of our model. Again, in machine learning, we care about predicting the future, and that's how we need to come up with our training, testing, and validation folds in general, and also that applies to cross-validation schemes. So scikit-learn does have a solution for this. It's called time series split. And there's a nifty little example of how it works. So this assumes that, for example, index 0 comes before index 1 sequentially. So fold 0, you would train on index 0, and then sequentially index 1 occurs and you would test on that. And then in fold 1, you train on index 0 and 1, and then you test on index 2, and so on and so forth. So this can definitely be very useful. However, there could be a situation where we want more control over these splits. And this could be because there are certain years that we want to make sure are grouped together. So if we were doing financial modeling, we may want to have certain splits that are aware of certain financial crisis or something along those lines. So there could be various reasons that we actually want to come up with these various splits. And I am not going to go into the construction of this function. You can definitely look at the code and get a feel for it. But the main point is that we actually can come up with these custom cross-validation splits. And this is not tied specifically to time series. There are other reasons that we might do this, and I will get into that later in this video as well. So one thing that I want to point out is that whenever we're doing a cross-validation score, here we're not tuning hyperparameters, but if we were doing grid search, or if we were doing something more sophisticated like hyperopt, which we will get into later in the series, there are these CV arguments that you will see, and most folks think that, okay, this takes a number, basically, so 3, 5, 7, 9, so on and so forth, but this can actually take multiple types of arguments, one of which is actually a list of tuples that include the indices for your cross-validation splits, and that'll be a little bit more concrete with an example. So what I'm going to start with is just kind of generating some random time series data. So we have a target, we have a predictor, and then we have a year. So what we want to do is create these custom cross-validation splits based on the year. So this function in this case is somewhat tethered to this specific use case. Obviously, this could be adapted for more generic purposes, but this is somewhat tethered to just splitting based on specific years. So we pass in our arguments and say, okay, this data starts at 1950, it ends at 2023, and we want to make sure that we have 5 folds that are as even as possible. So I will run this, and then this spits out our folds. So in this case, here is our first training fold, and here is our first testing fold. And then in fold number 2, this is our training data, and this is our testing data. So you can see, like in the scikit-learn example, our training set is getting longer, and we're just progressively sequentially adding to it. And we're, again, making sure that there is no overlap and that our validation set only includes data in the future. And you'll also notice that these indices are actually never trained on. So this can kind of be a holdout set, if you will. I would still, in general, recommend carving out a completely separate holdout set, because we could risk kind of overfitting to this fold here or different folds in the data set for that matter by running cross-validation, seeing what works, making adjustments to the data, and then kind of all of this data that has been used for any sort of validation within the training itself could, to a degree, get corrupted. This is called overfitting to the cross-validation set. And so we still generally want to hold out some data that is not involved in the training process at all and not involved with us kind of tweaking the model and playing with it. So that's just a little bit of an aside, but in this case, we're using all of the data for cross-validation, which is just as a sample, basically. So no longer need these print statements. And so now I can build my model. And again, we're just doing something very, very simple here. We're not even tuning hyperparameters. We're just saying, give me the cross-validation scores for these CV splits. And we can see that we get back our list of cross-validation scores. In this case, they are negative mean squared errors. So again, we don't have to just pass in 1, 3, well, I guess we wouldn't pass in 1, but 3, 5, 7, some other number here. This argument here is actually a lot more flexible. And so again, when we're doing cross-validation for time series, we have to make sure that we are doing it properly and not just assigning random data points to training and testing folds. All right. So there are other cases where we actually may want to do custom cross-validation. So this can often occur when we have something like panel data or we have some ID that appears multiple times in our data set. So for example, I'm just going to randomly generate a little bit of data here. So again, we have a target, we have a predictor, and then we have state. So we have Missouri, Kansas, Oklahoma, Iowa, and Illinois. I'm in the Midwest, so I'm favoring the Midwest here. This is a 500-row data frame. So something fairly simple. Again, this is just synthetic data. But since we have multiple observations for Kansas and multiple observations for, in fact, all of these states, what we actually probably want to do in cross-validation is train on certain states and then validate on other states, because we don't want to learn, say, a Missouri effect, because that really isn't indicative to predicting other states. Again, we may want to adjust how we're doing this based on the exact problem, but the overall example is that we don't necessarily want to learn some phenomenon that doesn't help us generalize. So there could be a situation, and this could be a modeling problem, where, hey, we actually want to learn on certain states and then validate that our learnings generalize to other states. And this could also deal with sports data, so we want our training set to only include certain players, and then we want to validate our model on other players. So again, based on the specific use case, we may adjust this a little bit, but again, there could be situations where we want to make sure that we are not mixing certain types of homogeneous data in our training and testing folds. So I will actually print what this looks like. In this case, I'm not going to actually build the model because we did that above, and it's just the same thing. We can just pass in the CV splits here. But this actually will then print out for each cross-validation fold which states we are training on and which states we are testing on. So in fold number 1, we are training on Illinois, Iowa, and Missouri, and we are testing on Oklahoma and Kansas. And then in the second fold, we are training on Oklahoma, Missouri, and Kansas, and then testing on Illinois and Iowa, and so on and so forth. So this is potentially, in this specific case, a way to ensure that our model is learning phenomena and relationships that are actually generalizable and is not just overfitting to some idiosyncrasy with a specific state or something along those lines. So again, there could be multiple reasons why we want to do this. But overall, the main point of this video is that we can actually do some pretty cool things with custom cross-validation that will help our model generalize and be the best possible model that we can fit. So I hope you found this interesting. This type of methodology is something that I've used multiple times throughout my career, and definitely something that I have found very useful in building models that can generalize.